slide. So what is the Zero Emissions Platform? So there are many ETIPs, and so the European Technology Innovation Platform, and the Zero Emissions Platform is one of them. We're really focused on CCS, and that falls under the European Strategic Energy Technology Plan, our SET plan, which has been in Brussels here already for, I think, around 15 years. And we are the official EU advisory body on the deployment and development of CCS and CCU technologies. So we have I think someone is not on mute. If he or she could mute themselves, would be great. And what's so special about the ZEP is twofold. Is that we are not only an ETIP, but we are also a membership organization since a long time, and we really have everyone on our platform, from NGOs to oil and gas companies, but also research bodies, and then companies actually being active in the supply chain of CCS. So really our very broad platform of those organizations involved in CCS for almost 2 decades now. Well, what do we do as a Zero Emission Platform? We have carved up our mission in 3 parts. So first of all, the overarching goal is for everyone is to reach the net zero ambition, net zero by 2050. And we really focus on the energy and industrial sectors, because this is where it gets hard to abate. So that means that you can only do so much with green electrons. There are just some sectors, and maybe also the power sector, for which you need CCS, and you cannot rely on renewable energy to become net zero. So we want to show that CCS is actually a really critical technology for this, and that also you can use some CCU, so carbon capture and utilization, to achieve the net zero target. And thirdly, and that's actually the phase that we're now getting in, is going from development to deployment of large-scale CO2 transport and storage networks. It's very important because you have the capture side and then the storage side. Those are 2 different things. And what we've seen now over the past 2 decades, that there has been a lot of plans on the table, but never really deployment. And as you'll see in a moment, is that now currently this market is really taking off. It's taking off too late. That is what everybody agrees, but it's now really happening. So especially this year, we've seen an enormous momentum for CCS technologies in Europe. So 2 very important sites in Europe have now reached their FID, so their final investment decision. In Norway, we have Northern Lights project, which will be offshore storage of CO2, which can also be imported from other countries. Actually was there, it was really, really impressive, and they will already become operational next year. And then just a month ago, the decision, or the final investment decision, was taken for the Porthos project, situated in the port of Rotterdam. So that's really about the North Sea basin, as you can see also on this map. In total, we have more than, I think, 77 market-ready CCS projects in Europe, all going to be online, or many of them by 2030. And then what also is in development is then the capture side. So, for instance, in Denmark, Ørsted is starting to construct 2 CCS facilities for the wood-chipped fired Asnæs, I hope I pronounced this correctly, power station in Kalundborg, and then the straw-fired unit at Avedøre power station in the Copenhagen area, which is a lot of combined use cases, including district heating. So this is really now getting from a pipe dream to actually reality. So it's very important to note that this is really not some kind of technology that is still in the waiting room, but it's actually now being deployed. And that deployment is actually really necessary, because if we look at the figures and the graphs, and I guess that a lot of you have followed the COP28 discussions, is that the world is not on track to achieve climate neutrality by 2050, and that also in the EU the CO2 reductions are not going fast enough, so we'll actually go to an overshoot of as you can see here, in 2050 we should be at zero, literally at zero, net zero emissions, and according to the EU policies that are currently on the table and agreed, we only get we will still be in the range of 1.5 to 2 gigatons of CO2 per year. And that's of course not sufficient to stay away from 1.5, the 1.5 limit, and also the 2-degree limit is not there yet. If you translate that into what kind of storage is needed, because really the storage of CO2 should only be for those sectors, as I already said, that cannot be cleaned up in a traditional way. So CCS, and everybody recognizes that the EIA, the European Commission, the IPCC, that CCS really is critical to reach climate neutrality. And that then also BECCS, so the bioenergy and CCS is also super important, also in the context of net negative emissions, which means that we can use this bioenergy CCS to take CO2 in fact out of the air, and then without explain in a moment. The latest news that came in just a minute ago, that I don't know if you've heard about the NECP, so those are the national energy and climate plans of member states. They have to review those, and in those plans they have to tell the Commission how they want to achieve their own climate targets by 2030. Several countries are now actually putting CCS in that mix of solutions, and according to the latest pledges, is that member states want to capture 34 million tons of CO2 annually by 2030, and actually of that 34 million ton, this includes 5.1 million ton from biogenic sources, and that is almost in line with the target that is set in the Net Zero Industry Act, that stipulates that Europe should have an injection capacity target of 50 million tons annually by 2030. So this act is very important because it can really resolve the chicken and egg situation that we now have. Because let's say if you are a paper industry and you want to capture your CO2, then you must also have a way to actually deposit the CO2 to get rid of it, because CO2 is not a commercial product, it's a waste product. So we're really talking about a waste management here, and that is fundamentally different from the energy question, I'd say, the energy market as such. To get to renewables, we're really talking about CO2 as a waste product. So a lot of capture sites, potential capture sites, will not invest in the technology, which can cost hundreds of millions of euros just to install the capture technology, and then also a lot of costs to run those capture technologies, and they will not invest that money in case there is no way to actually get rid of the CO2, and that means storing it a few kilometers into the ground. So that's why the EU now came up with this storage target. So how do we get to this 50 million tons, and then potentially already later hundreds of millions of tons of CO2 storage potential in Europe? From a geological perspective, entirely doable. So we can actually store probably billions of tons of CO2 into the ground in Europe very safely, very good geological formations, including in member states where currently the local population is hesitant about such solutions. I mentioned Germany, I mentioned Austria, I mentioned Spain, for instance. So what is very important is that we have a cross-border European CO2 infrastructure, and that can really allow the CO2 emitters across Europe to connect and secure CO2 storage. Secondly, as in with many European policies or market developments, there should be an enabling policy framework, making it economically feasible for companies to invest in all parts along the CCS value chain. Thirdly, we need incentives to really support the timely large-scale deployment of all parts along the value chain, including but not limited to revisions of the ETS directive, which has now happened, and that also that the EU national funding programs are coherent and coordinated. There's now some efforts on that in the STEP regulation, but more can be done here. And fourthly, a strong and continued support for the CCUS research and innovation, and that is through Horizon Europe programs and partnership within, for instance, the Innovation Fund, but also actually the ETIPs that are funded through Horizon Europe. This is critical support. Just click mine. There we are. Okay, zooming in then on BECCS or bioenergy with CCS. How does it work? Well, BECCS sorry, means that the biomass that is used for energy purposes, making use of some of the solar energy that was then actually stored in photosynthesis. And that is actually, if you do this well, it's some kind of carbon dioxide removal, and it also has the energy, production as a co-benefit. It's a bit theoretic here. If you have one moment, I have lost my mouse. There it is. So I'm just saying that BECCS is a form of carbon dioxide removal with the energy production as almost like a co-benefit, not as the primary, let's say, use case. Because the carbon is then of course through photosynthesis stored and then bound in biomass, and if you then burn a biomass and then you capture it, then you actually, without really releasing it back into the atmosphere, which is then the normal cycle, then you create negative emissions. That is at least the theory. This process is actually more energy efficient compared to direct air capture, as we will see in a moment. That's a very promising technology. You might have heard about that when you use really like big fans and other technologies to really filter the CO2 out of the air. But as the concentration of CO2 in the air, in the atmosphere, is very low, 420 parts per million, you'd have to have a lot of air going through these fans to capture it. And with bioenergy CCS, you have a much higher concentration of CO2 in the gases coming out of the factories. Yes. So, what is the goal of the Commission? So the Commission wants to actually remove and have a specific goal to remove and store CO2, 5 million tons of CO2 from the atmosphere annually by 2030. So this is not the process that is from let's say the normal carbon capture. For instance, if you were going to burn or create cement, because cement is a very large, the cement industry is a very large emitter of CO2 because of the carbon content in limestone that is burned at 1400 degrees. No, we're really talking here about the removal of CO2 from the atmosphere, and then BECCS can actually be, let's say, the stepping stone for that. Currently, so we're talking about 5 million tons as a target, but actually more than 200 million tons of biogenic CO2 is emitted annually in Europe. And where does this come from? From power and heat generation, but also the pulp and paper sectors, and then biogas. So here really is a lot of potential. I'm not sure here what percentage comes from waste incineration, because also I know that the waste sector has a lot of carbon content in there, but this is something maybe we can discuss later. And where does this need to happen? Well, mainly in Western and Northern Europe, you see the greatest potential for BECCS deployment, also because there's a lot of application of bioenergy industries there, a lot of presence there. And I think 40% of the CO2 emissions from industrial sectors actually comes from within 500 kilometers of the North Sea region. But that said, there is still a lot of costs involved. We have gaps in the infrastructure. There's also a limitation in the sustainable biomass stream. We have questions about the conflicting usage of the biomass, social acceptance, and also then the political feasibility. So on paper and in theory, it could work, but in reality, there are lots of hindrances from a full development of BECCS, bio-CCS, and without then actually also having a further burden on our planet. So looking at the capture map here, where you can see the biogenic CO2 capture in Europe and the emissions from biomass and bioenergy facilities. Here again, you see on the right these big bulbs, so you see where the emissions come from. So indeed, it's mainly a lot of activities in Western Europe. Ethanol plants usually have 70% of biogenic CO2. For biomass power plants, it can go anywhere from 0 to 100%. And then you also have the waste to energy plants, and there the average is 50% biogenic. Okay, so here you go. Yeah, then one project example is in Hafslund, Oslo Celsius, Klimetsrud, and actually Hafslund is one of the members of ZEP. And then cement plants are also having a lot of biogenic CO2. In total, we have 93 cement plants in Europe. One of our members is Heidelberg Materials, and they want to repurpose or fit CCS on all their 50 plants, I think, in Europe, and it is really an enormous investment that's needed. But Heidelberg is actually now also promoting a cement that is net zero, actually. So this is possible. Looking at pulp and paper, we have there 188 facilities emitting a total of 88 million tons of CO2 in the year. And then for food and industry, it's much lower, about 400,000 tons of CO2. What are carbon dioxide removals? Because if you want to create a market and a framework, you always start with the definition. So I'm not going to read it out all here because you can read it, and those slides will be shared with you afterwards, so we can look at this at each. But basically, carbon removals really refer to different techniques to physically remove carbon from the atmosphere and to store it out of the atmosphere in the midterm intended to be permanent. And in these processes, it's important to take into account all the upstream and downstream emissions. And that means you need really a full life cycle analysis, and that actually you come up with a negative sum, and that the efforts that you take actually result in lower atmospheric concentrations of CO2. So another process that comply with this definition, we can distinguish between direct and indirect processes. So the direct processes is the direct air capture from air. So that's the one I already referred to. But in indirect carbon removal, the CO2 emissions from biomass combustion are captured and stored. So this is really BECCS, and that creates a removal of carbon, because otherwise it would just go back. If you burn a tree, the CO2 goes back into the atmosphere, and you're in this cycle. The permanence is also something that is very important. So storage needs to be done in geological formations, but you can also put the CO2 into building materials. And now the Commission is actually working on a delicate act to define what the permanence is, and also in the carbon dioxide removal framework, which is now under negotiation at the Parliament. We see different definitions flying around about the permanence. I think I'll skip here the other, because we don't have so much time anymore. Just if you want to have more information, well, you can always contact us. But we recently launched as a ZEP, as Zero Emissions Platform, a report on CCS and biodiversity and land use perspective. And the other one was about the definition of carbon removals that I just briefly mentioned, that the Commission is now also working on. I would like to leave it at that. You can see my mail address, and happy to looking forward to the other contributions and the discussion in about an hour. Thank you.
Thank you very much, Joop. Thanks a lot. So just if there would be a question for clarification, we could take it immediately. Everyone at the bottom right of your screen, you have an option to raise your hand. But if there's no questions needed for clarification, then we will. I see one hand raised, so let's take that one. Luke.
Hi.
So you have a question for clarification, Luke?
Yeah, it's just a question for clarification. So thanks, you have very interesting presentation. You mentioned at a certain point that there was more than 200 million tons of biogenic CO2 available in Europe. And then in a few slides later, you said it was mentioned 45 million tons. Is the 45 million tons like point source with larger facilities, or what's the difference between the two?
Let me quickly look it up. Yeah, I think it's neat point source, but it's something I should check with my team how this actually adds up. That's a good point.
Okay, thank you.
Yeah. Okay, so yeah.
So this one we can deliver afterwards and see, but it seems to be the point sources that sum up to 45 million tons, whereas all of the biogenic CO2 is much larger. Thank you. So with this, I would like to turn to our next speaker, which is Alana Paul of Bellona, and she is CDR Research and Technology Advisor at Bellona Europe, and will point us to some points of attention for the deployment of bio-CCS. Alana, the floor is yours.
Thanks, Dina. I'll just check that I'm sharing the screen in the right way with you all. One moment. Can you let me know when you see the presentation?
Yes, we see the presentation in presentation mode. Looks perfect.
Perfect. Okay, one moment. So thanks for the introduction, and thanks for the great introduction, Joop. There's many aspects that I would like to pick up on and maybe expand on a bit in my presentation today. Thinking more systemically about the sustainable and credible deployment of bio-CCS, in particular, using it to reduce emissions from hard-to-abate sectors, for example, in cement, and capturing and storing the carbon for long periods of time, perhaps rather than particularly focusing on CDR as a primary benefit. So seeing CDR as maybe a co-benefit of bio-CCS rather than the main goal. So just a bit about Bellona, just to bring everybody up onto the same page. Bellona is an international and independent non-governmental organization that's working to combat climate change. So we have over 30 years of experience between the offices in Brussels, Berlin, which has just recently opened, and in Oslo. And we collaborate quite actively with civil society, academia, governments, institutions, and industry. And we try to bring kind of a systems thinking to the work that we do and to utilize the best available science and bring that to the foreground of our work. So with that, I'll move on to the content of today's talk. And so this is to think about bio-CCS systemically to enable the sustainable and credible use of the resources that are needed to, so we're talking about natural, physical, or financial resources that it requires, because all of these are very limited within the Earth system we work in. So this could be in terms of the CDR portfolio that it may be a part of, but also the deployment in terms of the realistic scalable potential that it may have some limitations. And endanger planetary boundaries. So we need to keep that in mind, and sustainable feedstock will be important in this. So to think about bio-CCS first in the CDR portfolio, just to remind you, I'm pretty sure you're all aware, considering the latest developments at COP, that action to cut emissions has been particularly slow. So we're not on the path to keep global warming below 1.5 degrees at the moment. And there are significant emissions gaps between current policies and the pathway to limit warming to 1.5 degrees. Most of the work to decarbonize the society will happen through traditional mitigation technologies, but there will also be a small role for carbon removals to, for example, tackle residual emissions in those hard-to-abate sectors. And the remaining carbon budget is being rapidly consumed, so we need to think about how to deploy these technologies at scale as soon as possible. So bio-CCS in the portfolio of carbon dioxide removal methods. So Jorp gave a nice presentation before about 4 key principles for carbon dioxide removal. Firstly, that you actively remove or physically remove carbon dioxide from the atmosphere. Secondly, that you store it in a way that is permanent. And the other 2 principles are related to the accounting side aspects. So here I'm showing you from the IPCC report the suite of different methods. They utilize biological capturing through photosynthesis. There is also DAX, which uses chemical removal, enhanced weathering, for example, as a geochemical example. And there's different mediums that you can store this removed carbon in. So there's many different approaches, different ways to capture and store the carbon, but these all come with different resource requirements for land, energy, natural resources, as well as the different lengths of storage or permanence of storage that is possible. For example, in geological formations or minerals, we're talking about tens of thousands of years or even longer. In biomass, in vegetation, soils and sediments, you're looking at more decades to centuries. So when we look at the bio-CCS system, we're talking about atmospheric extraction of carbon dioxide via photosynthesis. This is then cultivated. You have some emissions. So the light blue, just for context, is the captured carbon through photosynthesis, and you can see it following through the chain down to the end where it is stored in geological storage sites. Down the bottom in black, you can see, or dark blue, you can see what fossil fuel inputs there are into the system. And this is it should be taken as a quantitative assessment, but it's to indicate where there are emissions and leakages of carbon throughout the supply chain, from cultivation and land use, biomass harvest, transport and processing, carbon capture, transport and injection. And some particular advantages and disadvantages of bio-CCS combine both those of biomass use itself and of carbon capture and storage. So producing energy is certainly one advantage, both in heat and electricity. The bio-CCS permanently stores carbon, and it also has a low footprint on fossil fuel resource use and minerals and metal demands compared to many other approaches such as DAX. There are some disadvantages. The disadvantages, for example, the land use that is needed for, or the land area that is needed for the biomass production could present a potential conflict with food production or arable land and conservation goals, such as to meet biodiversity goals. It requires, therefore, a sustainable feedstock or biomass source. This can come from many different options, which I'll refer to in a moment. And like you mentioned as well, it requires the transport of captured carbon to storage, because often where the carbon is captured is not necessarily close by to storage sites. So there needs to be quite costly infrastructure built to be able to accommodate this. Nevertheless, bio-CCS could make an important contribution to the portfolio of carbon dioxide removal in future and help to reach net zero goals. So here I'm showing you a range of different scenarios. So we are looking at the IEA net zero emissions. There is an IAMC 1.5 degree scenario, which is a median. So these are some of the scenarios that were put into the IPCC calculations. And on the left, I'm showing you the potential, or there's a couple of different scenarios that were produced as a part of the NEGM Horizon 2020 project that was looking at quantifying negative emissions technologies. And they had one scenario that looked at advanced technology in global markets, which is basically cost and tech optimized, which is this 1.5 tech on the left. And the 1.5 ENV is the environmental scenario that they developed that prioritized nature conservation and biodiversity and didn't allow any additional pressure to be placed on the planetary boundaries. And you can see that with the estimates of bio-CCS, there's between, say, about 1.5 and about 4 gigatons of carbon that could potentially be removed by 2050. Sorry, I forgot to put that on the side here, but this is for, these estimates are for 2050. And then green, you can see the total CDR that is estimated from these different scenarios. This is about the range of what residual emissions estimates are in, so around 10 to 12 gigatons per year. If we look at a focus on decarbonization, so ambitious decarbonization. But bio-CCS certainly has quite a measurable role to play in the removals portfolio that is foreseen in the future and is the basis of many of the IPCC scenarios that are produced. So there is certainly a need for bio-CCS in terms of removing and storing carbon for long periods of time. But if we take a step back and think about the systemic resource constraints that may be placed, we've already heard about some of these from York with the geological storage capacity that will be required. But of course, more bio-CCS will mean more sustainably sourced feedstock and biomass in addition. So when we talk about sustainable biomass, if we wanted to convert any of the semi-natural or natural ecosystem or land that is used, that is semi-natural vegetation at the moment, to dedicated bioenergy crops, this would certainly exacerbate pressure on freshwater resources, the integrity of the biosphere, influence land system changes and the flow of, for example, nitrogen and phosphorus in terms of their biogeochemistry through ecosystems. And this is particularly true for irrigated crops. And this work has been carried out, these scenarios, I mean, much of this is common knowledge, but these specific CDR potentials from biocide streams are utilized from the NEGM project. So there are collaborators, Constanze Werner and other scientists from PIC have done a literature review to see how much energy could be produced from biomass side streams, residues, waste from, say, example, municipal solid waste, manure, forestry residues or agricultural residues that could enable us to retain, to not expand upon the land that is used for bioenergy crops. So as an alternative bioenergy source. These have a huge uncertainty associated with them and will be competing with other uses of these residues or wastes. But they could be quite substantial. If you look at these as an upper ceiling, we're looking at about 5 gigatons of carbon dioxide that could be removed from these residues alone. So there are other options that could be available that could be perhaps more sustainable than dedicating land specifically to those crops. And there's also ways to free up land, for example, by changing diets towards more plant-based diets that could free up some of the agricultural land currently used for food production as a way to not place extra pressure on the land area, but to still provide extra biomass to be utilized, for example, as bio-CCS. We need to see these as upper ceilings rather than a goal or an ambition. So that's just one thing to keep in mind when I'm talking about these numbers here. And of course, there's potential for competing interest for the residues and side streams as well. A second aspect is, of course, the geological storage capacity. There are big plans to be able to upscale this. Right now, we're looking at about 44 million tons of carbon dioxide per year. And on the right-hand side, this figure shows you the cumulative installed CCS capacity since the 1970s. So it does look to be exponential in terms of its growth. In the pipeline, there's about 250 million tons of CO2 storage capacity planned. But this could, of course, be a bottleneck potentially for the scale-up of bio-CCS. And in general, there will be a lack of storage for carbon, both in point source capture as well as using CCS related to bio-CCS or DACs. So what about bio-CCS today? Current planned applications include, for example, heat power plants, cement plants, pulp, paper mills, and hydrogen production. But in terms of thinking of what would make a credible bio-CCS project, we at Bologna think that we need to think about the sustainable biomass streams that are being put into its bio-CCS should be used primarily to replace the use of fossil fuels. So we don't want to use biomass here to displace the use of renewable energy sources, and we don't want to use biomass as a way to replace, for example, where direct electrification could be more efficient. And then if you think about, where could you apply bio-CCS as a priority? I mean, to put this more clearly, we already use biomass in many different ways, some of which I highlighted before, and we need to think if we're using biomass in the best way, and not just biomass in the best way, but to think about, do we need perhaps even a cascade of biomass combustion, for example, between heat generation, electricity, or other sectors, because it will be limiting in terms of the amount that is available. So we want to ensure that it doesn't get used for sectors, for example, where zero carbon alternatives such as direct electrification already exist. I think I can hear somebody with the microphone on. If you could put it on mute, that would be much appreciated. And when we come to the carbon, we need to think of the CDR system or the carbon dioxide removal system boundaries and ensure that whatever activity we are doing, we are removing more carbon than what is being emitted through the activities themselves. So more is being sequestered, more is being stored, rather than remaining in the atmosphere. So this is a way of ensuring that we have a physical climate benefit, which means minimizing all of the greenhouse gas emissions. I'm going to pose a question here to consider, and it's something that we can maybe discuss after this, the series of presentations, if we need to revisit or revise the zero rating of biomass. Current capture is about 2 million tons of CO2 per year, but less than 50% of this is stored in dedicated storage, and some of it is utilized in different ways. I mean, bioethanol is the primary use of bio-CCS, as far as I'm aware at the moment. And so I think we need to ensure that whatever incentives we have, we ensure that the carbon from biomass utilization is captured, and that the overall goal and the incentives that are there are used to support emissions reductions and preventing the carbon being emitted to the atmosphere to begin with. And so this is related to the zero rating because these are usually not tracked at the moment in terms of how much carbon is emitted through the combustion, because it is seen to be basically carbon neutral, this biomass that is utilized. And so there isn't really an incentive to actually capture the carbon from that biomass to begin with. So I just want to summarize these different systemic considerations. Bio-CCS will be a number of numerous ways to remove and store carbon permanently. And so we need to think about it within the Earth system for both its benefits and its impacts. So in terms of its contribution to the carbon dioxide removal portfolio, to think about what biomass do we want to allocate or feedstocks that are sustainably produced for that purpose. to consider potential limitations on the upscaling due to pressure on planetary boundaries that are already under quite extreme pressure, and to ensure that it's used to displace fossil fuels rather than replacing other renewable energy resources. And I'd like to wrap up with some recommendations from our side to consider the best use of biomass in side streams, in particular for combustion, maybe to think about a cascade of different uses, like was already done for biomass utilization, to ensure that we use positive incentives to ensure all carbon is captured, regardless of its origin, regardless if it is from biogenic sources or from fossil fuel sources, because preventing carbon being emitted to the atmosphere to begin with is better than trying to suck it out using more expensive, more costly processes later on. And then to think about managing our expectations on the overall scale of bio-CCS for removing carbon. And finally, I want to introduce the carbon accounting team at Bellona. So there's Mark, myself, and Irene. And I thank you for your attention, and I welcome any questions you have, and I look forward to the other presentations and the discussion afterwards.
Thank you very much, Alana. Very nice presentation. Let me just put on my camera again. Thank you. So that was a perfectly clear presentation to me, but nevertheless, there might be the need for one clarifying question. So if so, you can use, put up your hand at the bottom right of the screen. Let me check, but I don't see any hand raised here. So Alana, you will stay with us for the discussion, and we will have plenty of time to discuss and pose some questions to you. Thank you very much.
Thank you. I look forward to the discussion.
Perfect. So with this, we turn to the next speaker, which is Jannike Bjerkas of Havslund Celsio. And I believe your project has already been mentioned in the previous presentations. So this is one of the industry examples on the CO2 capture on Norway's largest energy from waste plant. And Jannike is Director, CCS and Carbon Markets in Havslund, also Celsio. So Jannike, welcome, and the floor is yours.
Thank you very much. I hope you all can hear me and see my screen.
Yes, perfect.
Good. So my name is Jannike. I'm working with carbon capture and storage in Celsio, and I'm currently working with business development and carbon markets. To start, just with a few words about the company Celsio. We are an energy company and waste incineration company, where the waste incineration, the heat from the waste incineration, is the main heat load into the district heating system in Oslo. And this system is providing about 20% of the total heat demand in the city. We're also building up area cooling and CCS full scale on this waste to energy plant, the largest waste to energy plant in Norway. And we're also working in fiber and electricity. To look at the big pictures, let's start with the big picture when it comes to waste. And waste is definitely one of the world's biggest climate challenges, and maybe also one of the challenges that we don't talk enough about. With cities growing, people moving to cities, we also see waste amounts increasing. Even though we're working to reduce it, waste is increasing. And 2 billion tons of waste is produced every year, and it's estimated to increase to about 3.5 billion tons just by 2035. So this is a huge problem. And with landfills being the main solution for waste handling in the world, methane from these landfills are actually accountable for more than 20% of the global warming effect. And this has also been a topic at the COP going on right now to reduce methane emissions, which is a very potent climate gas, much stronger than CO2. So we need to avoid methane emissions from landfills, but we also need to work to reduce and reuse and recycle the waste to keep the resources in the cycle. But for the residuals that we cannot or that we don't want to recycle, we need to incinerate it with energy recovery And then by adding CCS to waste to energy or waste incineration, we can both reduce the fossil emissions and also remove the biogenic emissions from this process. CCS will be the next step in the circular economy and a valuable tool to reduce these emissions from the end-of-line solution for waste. And it's important to keep in mind, just as Joep also underlined, that CO2 is actually a waste product that we need to get rid of. And looking into waste, we also need to talk about plastic. Plastic is also a major challenge with enormous amounts produced every year, more than 6 billion tons produced globally, and only 9% of it being recycled. So this is, and we know that the plastic that is not recycled or incinerated is ending up as microplastics in oceans, in rivers, and in the ground. So this is a challenge that needs to be addressed. Plastic is also difficult because it's only a small proportion of the plastic that is actually possible to reuse or recycle. After it has been recycled a number of times, it needs to be taken out of the cycle because it is contaminated or really bad quality. And with 12 billion tons of plastic lost in 2050 is the estimation, we really need to address this issue. And waste to energy with CCS actually deals with this problem and eliminates the non-recyclable plastics and handles the CO2 emissions from this plastic. Now, the main action to reduce climate emissions is obviously to reduce fossil emissions, but this is going way too slow. And that's why we also need carbon removals to speed up reductions and to remove historic emissions. And with energy from waste or waste incineration, having about 50% of the CO2 emissions from this process is biogenic, this industry can actually contribute with substantial amounts of CO2 removals. Now let's look at our project. We are still hoping, even with a few setbacks the last year, to be the world's first full-scale CCS project on waste to energy. We are part of the Norwegian value chain for carbon capture and permanent storage of CO2 called Longship. And in this value chain, there are two capture projects, one from cement and one from waste incineration, which is our project. We started constructions in 2022, but as mentioned, we have had some setbacks. I will get back to that. So we don't really know right now when we will conclude or when we will start operations, but the goal is now 2028. We're planning to capture 350,000 tons per year of CO2, which is 90% of the total emissions from this process. And as I mentioned, with 50% of this CO2 emissions being biogenic, it's a large potential for carbon removals. This project is a public-private partnership with contributions both from the Norwegian state, from the city of Oslo, and from the company itself. But from the state support is deducted CO2 taxes and also possible income from carbon removals for the first 10 years, which is the support period. These numbers are already outdated, as I mentioned, since we have had to pause the project. And this is due to cost increases or increases in cost estimates. During the fall, we started the project last summer, 2022. We finally reached an investment decision with new owners and started the project in August 23. However, during the fall, due to inflation, really high inflation, high power prices, high interest rates, and a very bad currency on the Norwegian crown, we suffered cost estimates that was skyrocketing. In addition to this, we had the complexities in the project, both including that we needed to change the location at the port of Oslo. We needed more area, more land at the site, and we also had challenges with the local power demand. With all these complexities, we also needed to increase our own organization. So this caused an increase in cost estimates, which led us outside the budget frame. So we paused the project in April this year. And as I mentioned, the goal is to restart the project with a new investment decision next summer. During this pause, we are working with, obviously, with maturing the immature parts with land and at port. But we're also working to find revenues to cover this substantial company contribution of more than 400 million euros. As part of this change, we have also decided to conduct a new feed study, and this study will be executed by Aker Carbon Capture and Aker Solutions. The feed will go until June next year, with the goal to have an investment decision next summer, and it's based on Aker Carbon Capture's Just Catch module of 400,000 tons. The key enablers for our project is obviously partial state funding, as mentioned, and also a contribution from the city, because these emissions are actually the largest point emissions in the city is this plant, and these emissions count for about 17% of the city's emissions. So capturing and storing these emissions will contribute to the city reaching its climate goals. In addition to this, avoided costs is a part of the picture. With we have a separate CO2 tax in Norway, and we're also inbound in the ETS system from 2028. And then on the revenue side, carbon removal certificates will be very important to manage to actually succeed with a new investment decision. We see market prices today of around 200 euros for bioenergy with CCS, but there is a need for a framework and a methodology to address issues like the biogenic content, that it's measured and documented, a certain traceability on the waste side with the requirements for sorting and so on, and that the CO2 is actually stored permanently. And if we look at how this market will develop, we truly believe that this will be an increasingly important market in the years to come. This is the Norwegian Center for Scientific Research, which has stated that it's not even theoretically possible to reach the 1.5 degree target. And let's look at this graph a little closer. Now, this graph already shows that we are about to exceed the 1.5 degree target, and we're doing it very soon and fast. We also see that 2023 will be the hottest year ever registered. So these are scary numbers. And in addition to this, we know that a lot of the stored of heat is already stored in the ocean, which also contributes to accelerate this development. And the bad news is also that the increase we see in renewable energy production is mostly in addition to the fossil energy and not replacing the fossil energy. So there's a lot of work still to be done on the energy side to reduce fossil emissions. And time is running out even for the possibility to reach the 2 degree target. We're looking at a massive overshoot, as you've also stated, and this is also a reason why we know that carbon removals will be of large importance to reach the climate goals, both to speed up the reductions, to balance the hard to abate emissions at net zero, and also to, after the overshoot, to get back to the levels about 1.5 degrees after we reach net zeros. But it's important that the prices for carbon removals must be higher than the price of reductions, because this cannot be the easy way out. We first and foremost have to reduce the fossil emissions that are possible to reduce, and then we need to add the carbon removals on top of that. with regards to the waste to energy or waste incineration, we know that it's possible to measure the C14 component in the flue gas to actually document the exact level of biogenic CO2. So this is not a big challenge. It's also documented that just the capacity we have today on the waste to energy side in Europe can remove 35 million tons of CO2 if it is equipped with CCS. So this is a substantial contribution to Europe's climate goal. And also with waste incineration, we don't really need this difficult discussion when it comes to the origin and the sustainability of the biomass, because this is low quality waste that has been sorted. It's not really, it doesn't have any other use. So it's biogenic CO2 just waiting to be captured. We see that customers today are the early movers. They are content on securing future volumes because they know that demand will rise and they want to secure their options by entering this market early. And our goal is to realize parts of this BECCS volume from our plant before the new investment decision. So we are working really hard and we are contacting customers, potential customers, and everyone who should be a customer in order to get this market started. So to conclude, waste to energy with CCS is actually a 3-in-1 solution, which is what we in Norway call a kinder egg. It's a chocolate, it's a surprise, and it's also a toy. For our part, it provides safe and sustainable end treatment for the unrecyclable waste that has to be taken out of the cycle. It also produces heat and electricity, and it contributes to removing CO2 from the atmosphere. So as soon as we have the framework in place to actually include this market or these certificates in the compliance market, this will really it will really be possible to reach high volumes in this market. Thank you.
Thank you very much, Jannike. This was a very interesting presentation. I do hope that you will have green light to continue with the project very soon, that the framework will be set up in a way that it allows you to go forward with your project, and not only with this one, but of course with entire suite of projects from your company and other companies.
Thank you very much. We hope so too.
Yes. So I see that our next speaker still has troubles in connecting and getting the audio system working, which means that first of all, we can take a clarifying question if there is any, or even a direct question. Jens, do we hear you now?
Let's see, I'm on the phone in here.
Yeah.
Can you guys hear me?
Oh, yes, that's perfect.
Okay, well then, well, I tried all my different browsers I have. Nothing seemed to work. So I guess we need to do it through the dial-in. You guys can't see me, but I guess that's fine as long as you can see the presentation.
Okay, yes, this will be fine. So then just give us a moment to see whether there's a clarifying question to Jannike, and if not, we're gonna share your slides from our computer and give you the floor. But
Perfect.
If anyone has a question to Jannike needed for clarification, I don't see anyone. Okay, thank you, Jannike. We will see you again after the fourth presentation. So now we turn to Jens Fuhrmann, who is head of strategic development of BECCS at RWE Generation. And yeah, the slides are there already as well. Jens, over to you and your company's project.
Okay, thank you. Can you guys hear me fine?
Yes, we can hear you fine.
Okay,
Are you sharing the slides yourself, or is my colleague doing for you?
I'm sharing the slides.
Okay, because it's not yet presentation mode.
Yes, I know.
Actually, I cannot see any slides, so I'm just gonna talk whenever you give me the sign that the slides are on, and then I hope that you can just click through based on what I say.
Sure, we will manage. Sorry that you had problems with connecting, but I'm sure this is going to work out.
So now at least everybody else should see the slides, right?
Yes, yes, we are. Perfect.
Cool.
So Jens, the floor is yours.
Okay, thanks a lot. Yeah, so maybe first of all, my name is Jens Fuhrmann. I work for RWE now for some 11 years or so, and now the last 2 years as head of strategic development of our BECS ambitions. And maybe for those of you who don't know RWE that well, RWE comes from a history as being Europe's biggest energy producer, or one of Europe's biggest energy producers. But in our history, we're also actually one of the biggest CO2 emitters in Europe. And by now we have a very ambitious strategy, which is our Growing Green strategy, and that has just been revised a couple of weeks ago again when as part of our capital market day. And now we've even raised our ambitions. So the main ambition is to be CO2 neutral by 2040 as a company in a whole. And to get there, actually, we even increase our investments. We will, starting from next year until 2030, we will invest some 55 billion euros in mainly renewable capacity build-out. We will then be at a sustainable capacity of around 65 gigawatts in 2030, and we have some 100 gigawatts pipeline that we're working on to really deploy this. Basically, that's a build-out of more than 4 gigawatts a year that we're looking at to reach our target. This is then RWE in a nutshell. And we'll go to the next slide. If you look at the energy system in total, like a lot of people are, of course, focused very much to the energy transition, but it's not only the energy transition in itself, but it's also the materials transition. But to get there, of course, a big focus also for our company is on the wind build-out. Wind and solar, that is, of course, the workhorses of the energy transition. But it is not only wind and solar, but of course we need to make sure that we also have a secure and affordable energy mix in the future. And that's also something that the recent events in the last 2 years have shown, where we had quite cheap energy before, also with natural gas, which was always considered to be a bridging technology. Well, now we have seen that not everything is secure, and especially not everything is affordable. So that is something that we can also deliver into the system. At the same time, of course, everything what we do needs to be sustainable, because only if it's sustainable, it is something that we can also hand over to our future generations, and that's also part of our mission as RWE. And if you look into it, the real challenge that we faced as being one of the biggest producer of electrons and then basically green electrons is that, of course, it's not only the volatile energy that you need, but you need to take a very big step on system integration. And that includes, of course, to not only have volatile solar and wind, but also CO2-free dispatchable power, which is, of course, something that we can deliver with BECS at RWE. And of course, and that is one major topic that has been brought up also, or put into, actually basically everybody's mind, also of the politicians, is that not only the energy system needs to be neutral, but actually the energy system even needs to go negative, because only the energy system can really help them in that way to help other sectors to become CO2 neutral with their hard to abate or not to abate emissions. So the bottom line of the whole thing is that basically the electricity system needs to grow by 400%, but at the same time we need to balance the other goals with that as well. And that brings me to my next slide, which is actually the CO2 emissions in a megaton per year equivalent of CO2. And this is a Dutch example. So this is the Dutch emissions starting from 1990, which of course was the baseline in the European Union for the 55% reduction target. So in the Netherlands, coming from 221 million tons of year of emissions, this means that in 2030, as a milestone on the way to climate neutrality, the country needs to go to 99 million tons in 2030. And the cabinet, which of course by now has fallen, but the cabinet has even raised the ambition, has said like, well, let's do 60% just to be on the safe side. So that would be 89 million tons per year that are still allowed to emit. However, if you look into the 2022 numbers, there's still some 150 megatons per year that are being emitted. So that means that within like 32 years, that approximately 70 megatons per year have been reduced on that pathway. But it also means that there's another 53 megatons to go within the next 7 years. And this is actually where then our ambition kicks in, which means not only reducing the emissions, but also actually being part of the solution to accompany the reduction with also carbon removals. And that brings us to my next slide, which is then our BECCS value chain. And you see on the value chain that we have some red boxes on there, and that is basically where we're active ourselves, which means that all of this is something that we can only do and be successful at if we do it together with partners. Because if you want to build this chain, which is actually in this combination a huge challenge on the infrastructural side, but also on the side to even basically build the markets, because these markets are not all there yet. So it starts on the left. What we need is, of course, sustainable biomass. As I pointed out before, the only way to get there is with sustainable biomass. We cannot afford that there will be any doubts about that, because in the end, of course, this target should be also in line with all other targets, be it on reforestation, but also biodiversity and everything else that's out there. And then in an ideal world, we're not basically insisting that we need to have that biomass right away, but we are happy if other companies and other partners take it and put it through biorefining, basically, to get some of those sugars out there that can be used for example, for products as well. But what is left over is usually then, kind of like the lignin-based stuff with a lot of carbon in there. And this is actually what we can really burn in our power stations. So what we're doing is we're converting our power stations, Ammer and Eemshaven, from coal to 100% sustainable biomass. And that, of course, is also a combination of doing two things. The one is really going from coal firing to biomass firing, but at the same time, or actually shortly afterwards, we're also going to add the carbon capture. And once you do the carbon capture behind it, coming from a biomass power station, that per definition is at zero emissions already, because it's basically then circular carbon going through the atmosphere. If you to put a capture behind it, of course, you can capture the green CO2, which you then have for two routes to go. And the one is, of course, the route to do negative emissions, which means shipping then basically into storage, can either be shipping or by pipeline. And then, of course, also, and we're coming from the right side of the chain here as well, with wind and solar being the workhorses of the energy transition, with the volatile energy. Of course, again, one part of the whole thing to handle it is to have some clever and smart system integration parts. And that is, of course, to also, for example, produce green hydrogen off it. So you've got green hydrogen, you've got green electrons, and now we have green CO2. If you put it together, you can pretty much make whatever product is needed in the world, be it a drop-in fuel for sustainable aviation or sustainable shipping, but also, of course, as base chemical also for the materials transition. And on the side, if you want to put it like that, we can still produce our CO2-free flex power. So the next slide is then a map of the Netherlands, where we can see the location of our two power stations. All the way in the north is our Eemshaven power station that was commissioned in 2015. So it's still a quite young power station that's only 8 years old. And it is a 2-unit power station that is originally designed for almost 1,600 megawatt electrical, and that we're now currently looking into converting to biomass. The first step has been taken. It is on 15%, so 15% biomass already. We have the permits in place to go to 30, and currently we're working on the 50% and the 100% conversion step. And also, of course, we're developing the carbon capture plant and also how to ship it out to afterwards be able to generate 8 to 10 megatons per year of negative emissions, and also, of course, supply green CO2 to the local industrial environment, which is quite close in the area where the power station also is, and close to Delfzijl also. And then we have one power station in the south, the Ammer power station, where this is Ammer 9, and we're seeing Ammer 9 also started off as coal-fired power station, was commissioned in 1993, so is 30 years old, which is also still quite okay and young for a coal-fired power station that can easily go with the right maintenance to be 60 years old in the end. So what we're doing here also, it's a single unit of 600 megawatts electrical, and that is sustainable and flexible power as well. In addition, we also have 350 megawatt thermal heating capacity for the local district heating, where we are covering more than 50,000 households in the vicinity of Geertruidenberg. And once converted to 100% biomass, it's on 85% biomass right now. Once it's converted to 100%, and then we also add the carbon capture, it can basically put 3 to 4 megatons of CO2 into storage per year, or provide it to the green industry, basically. And so if you add it up and you remember a little bit what the gap is to close also in the Netherlands as a milestone, well, we have 8 to 10 and 3 to 4, so basically 11 to 14 million tons of negative emissions that we could throw into the game only with these 2 power stations in the Netherlands to help the society to reach the targets. If we go to the next slide, I also brought some visualizations of the power station. This is our Eemshaven power station, all the way in the north of the Netherlands, where what you can see in the middle of the picture, say the blue structures in the middle of the picture, that is our Eemshaven power station as is. And then what you see is in yellow, you can see that there is some existing biomass equipment that's for the 15% conversion, and what is there in red and in green, that is the 50% biomass conversion step, and then 100% biomass conversion step, which basically consists of a change the logistics system with 2 new ship unloaders on the South Quay, where also that big ship is anchored in red, and then transporting it into 2 to-be-built biomass silos. These are like 65 meters high, and each of them is good to hold a capacity of roughly 65,000 tons of sustainable biomass, where from there it's going to be conveyed pneumatically into the power station to be fired. What you see on the top right side, actually in green on the former coal yards, is actually that we will need some dosing of fly ash to get the boiler chemistry right. So this is not coal, but it'll then be fly ash. And if we go to the next slide, this is then the situation once we've also added then the carbon capture and storage, which is now behind the power station, which will consist most probably of 2 trains, where both trains each will have 2 large absorber towers and 4 strippers behind it to capture the CO2 from the flue gas. So this is really the 100% setup. So basically all the flue is to be put through, not through the chimneys, but then through these absorber towers, which are like 17 meters in diameter and around 110, 120 meters high. If you jump to the next picture, the next slide, you can see a visualization of our Amer power station that is more to the south. And this first slide is the picture of the as-is situation. What you can still see here is that you also still have 3 chimneys here, only 1 being active. And if you go to the next slide afterwards, you can see that 2 of these chimneys have gone. So basically the back side of the old units of the power station will be demolished, and then we will have 1 train with 2 absorber towers that are then placed in between the older power station and the newer power station, with 2 strippers after that to be able to get the CO2 out of the flue gas and then put it most probably into the Delta Rhine corridor, which will then take it to Rotterdam and from there to the Aramis network. Maybe then real quick as a last slide on a very, very high level, just also to indicate when are we planning on doing that. You can keep in mind we're planning on doing this before 2030. So basically, finishing the whole conversion to 2030. This is now the Amer timeline. The Amer timeline starts with right now the fly ash dosing testing it. That's pretty much completed. 100% testing has been done. Next year, there will be the final setup for the biomass conversion. So Amer will be on 100% biomass by the end of next year, and work as a biomass power station from that time onwards. The carbon capture conversion is on a little bit longer timeline. So to develop this kind of large scale capture equipment, and also the infrastructure to take it from there, and basically, for example, in this case, to the Rotterdam area to take it then out into storage. That all takes some time. So we're looking into, well, the most ambitious way that we can think is that we will develop the whole project until the end of 2025, and then take the first FID, and then within 1 year the second FID, then allow 3 years construction and commissioning to be ready on 100% carbon capture and storage right before 2030. And then with a total of 14 megatons of negative emissions per year, we can be a significant and relevant part of the solution. Yeah, not only for the Dutch society, but for society in general. I think the last slide we can skip. What I did put on there is just for those who are technically interested, but I guess this is not new for people, is a very rough overview of how, of course, the carbon capture plant works, but I think we will not need this right now. So just, yeah, let's stick with the idea how 14 million tons of negative CO2 emissions can be part of the solution by 2030.
Thank you very much, Jens. Very interesting. Thanks a lot. So what a pity that we cannot see you, and the more that you cannot see the audience that we have here. Nevertheless, we have another 30 minutes that we can use for discussions. I would like to invite all the speakers to open up their cameras again. I would like to remind the audience that those who have joined in listen-only mode, which means instead of a microphone, you see the symbol of a headphone next to your name. You can reconnect the audio to get into the other mode, or of course you can pose your question in the chat, and we will also be able to pick it up from there. If you want to reconnect, at the bottom of your screen, just in the middle, there is a speaker symbol, and if you click there, you can reconnect. So I already see Alana and Janneke with her cameras on. Maybe Job, yes, he's coming on as well. I like the gender balance of this panel. And yeah, Monica, do you want to just briefly mention the Slido questions and how that works?
Yes, before everybody drops out, I would like to ask you to participate in our Slido that we get a bit of feedback on this webinar. But I do not want to disturb the discussion right now, Dina. I just want to make sure that not everybody drops out, and I would like to share a Slido that takes less than 5 minutes with you after the discussion.
So we will reserve the last 5 minutes, or maybe something like 10 to 4. We're gonna start with the Slido questions so that we can get some feedback from the audience, so that we can further improve our webinar series. Okay, so with this, I see all the panelists here. Anyone who wants to pose a question, you can raise your hand. There is a symbol of a hand on the bottom right of your screen. And you could also write in the chat. And if you can't find either of those, of course, I would also encourage you to just simply speak up. I see that we already have one hand raised, which is Luke Peltmans. Please, Luke, go ahead.
Thanks, Dina. I just had a clarifying question to Jens from RWE for the last presentation. Mm-hmm. It's 2 quite big power plants. Is Jens still online, or?
Yes, he's still online. He is on the phone. Yeah.
Okay. It's 2 quite big power plants, and you mentioned it's important to have dispatchable power. Are these intended as baseload operations in the longer term, or also have some flexibility, including the CCS?
Well, it depends. In the end, we will be operating in 2 markets at the same time, the one being the electricity market, the other one being the negative emission market. So talking from a negative emission market, you want to be maximizing your output. So you want to basically run a base load. However, we of course still are in that market of electricity where we will also deliver these flexible products. So that means that we will try to maximize production, but still allowing to deliver also the stability to the grid as intended for this.
Okay, thank you.
Okay, thank you. So far, I've seen no hands raised, so I'll give you some time to make up your questions. So we've been talking about carbon capture and storage for most of the time, but maybe Job, you could also help us understand what is the difference between the carbon capture storage and the carbon capture and utilization. So Job, maybe you can just briefly explain the differences between the two concepts.
Yes, indeed. There are two different concepts. The main challenge that we have is to get rid of the CO2 before we emit it, and that's really the carbon capture storage itself. That is the big challenge that we have. For a part, I think the ballpark figures are about 10% of that carbon that we capture. We can actually reutilize it as a feedstock for the chemical industry, to make sustainable aviation fuel, to use it for the food and drinks industry, and there are some other ways to use it, also for actually to make some building materials. This is a contentious topic because, for instance, in case you use the captured CO2 to make sustainable fuel, then in the end you'll be emitting the CO2, but then at a later stage at 10 kilometers altitude, where it actually is more damaging for the planet, because there's like a doubling of the climate impact when you burn fuels into the air at that altitude. That said, we are not, as the Zero Emissions Platform, against CCU, but there should be a full life cycle analysis of all the products. There should be a level of permanence. For instance, one thing that you can do is actually, when you make concrete, you can inject CO2 into the concrete and it is then stored. And there are also a few other use cases of CCS that have a certain kind of permanence in it there, and that it's not in the end then also then emitted. But it's important to really distinguish between CCS and CCU. Hope that helps.
Yes, thank you very much. And then maybe I would also like to ask Alana from the NGO perspective, do you see benefits for both of these CCU and CCS technologies, and where would you like to see each of them deployed?
If I can maybe respond to the first part of the question, I think it's important to make sure we clearly know and define the system, have an understanding of the physical carbon flows for whatever bioenergy or whatever CCU, CCS system or carbon removal system you're talking about, because they will, in essence, have very different impacts on where the carbon ends up, as you've referred to. And it's important to have a clear definition of the system to understand what is emitted during the activities, where does the carbon end up, how long is it stored for. There is certainly value in replacing fossil fuel use in carbon capture and utilization. There is certainly a use in capturing and storing the carbon, so it's stopping it being emitted to the atmosphere. And there's certainly a need for removing carbon from the atmosphere to meet our climate goals, to limit warming. And so there's a need for all three of them. It's a matter of figuring out which are the best, the most efficient ways of doing each of these different processes and ensuring that you're accounting for the carbon flows correctly in a broader sense. You know, you want to remove the carbon from the atmosphere and draw it down you want to stop it being emitted. And you need to think of like a larger system that you're working in to see where all of the inputs and outputs are coming from. I hope that answers your question. Yeah.
Yes, it does. Thank you. Thank you. And then I see we already have two questions in the chat. There is Nicholas Vidrago, but he is in listen-only mode, yes. So his question here is, and it refers to Jens Fuhrman, for the 2 power plants in the Netherlands. Did you mention what kind of sustainable biomass is used or will be used? Is it possible to use it to replace coal without too much conflict of use?
Yeah, so I think I didn't mention during the call, but well, the first thing, of course, it needs to be 100% sustainable. But then not only sustainable, but also we don't want to be into any conflict, for example, with food or cause deforestation or anything. So in the end, what we use is at the moment is mainly woody biomass. So that is then left over, so residues from wood production, from sustainably managed forests. So that's basically pellets that are made from sawdust, for example, from sawmills, and these kind of things. In the future, and we have done a lot of testing on that in the past already, is to replace more and more of the woody residues through agricultural residues, where, for example, we're looking into using bagasse, or actually bagasse, for example, that's the leftover of the sugarcane production, for example, in the south of the United States of America, Louisiana, for example. And well, then afterwards, also bagasse can be put to a second use, for example, that could be then second generation ethanol production. And what would then remain is lignin, which is basically the carbon skeleton of biomass that cannot chemically be used in any other operations. So we're quite flexible on what kind of biomass we could be using. For us, the most important thing, it needs to be sustainable, and it should be in a pelletized way so that we can manage to operate it with our logistics. And then the question was also, well, can we use it to replace coal? Well, the idea is, of course, to replace coal. So we will burn no coal at all anymore at both power stations. So it will be 100% biomass. And the conflict of use, I hope I just explained already. It is residues of the production of other sustainable materials.
Thank you very much. Thank you. And then I don't know who exactly will be able to answer this question. It's by Rahul Jain. He asks whether there are any algae-based carbon capture case studies at large scale, and whether this technology is eligible to get carbon credits. So anyone who has an answer to this about algae-based case studies?
So maybe I should explain, I have a background in oceanography, actually, so maybe I'm the best place to answer this question. I don't know, I mean, it depends on what you define as large scale. There are certainly plans for many to be deployed at large scale. And the idea being that they take up carbon dioxide from the atmosphere, and like a plant on land. The difference being here is that they take it up from seawater, so you actually rely on the atmosphere to equilibrate with the surface seawater for it to actually remove the carbon from the atmosphere. It's not direct like a plant on land. So that's an extra step that has to be considered. And I think in terms of being eligible to get carbon credits, it would depend which system you're working in. There may be people who are better informed on this than I am, but I would say it would depend on which country you're working in at the moment. There are some companies, I think, in the US that are working on that direction of getting carbon credits on the voluntary carbon market. But in terms of like a compliance market, I'm not aware of any, but maybe the other panelists are a bit more aware of the developments in that sense.
Thank you, Alana. So Rahul is also sending his thanks. Yeah, and we're talking microalgae or macroalgae, or does it make a difference then?
So both can, in theory, work. The macroalgae are easier to track if you're looking at monitoring, reporting, verification, because it's usually attached to the seafloor or it's in a set location. Microplankton, or plankton being that you float with seawater, that you move, you're free moving. It's a bit more difficult to track in that sense. But then you don't know where the carbon ends up. So again, it's knowing like where the carbon is, where it's being transported, where it is going through the food chain. And it's certainly easier with macrocarbon than it is with microplankton, like algae. But again, you rely on this exchange of carbon dioxide between the atmosphere and seawater, because the seawater acts basically as a sponge to take up the CO2 once it's been drawn down or incorporated into the algae themselves. Yeah.
Perfect, thank you. And then I guess if we think about microalgae, we would probably also think about land-based solutions where we have cultivation of microalgae, and then we need to provide the CO2 into the culture medium, so that would be done artificially then, and in that case not rely on that surface water exchange that you just described.
Yes, that's true. I guess it depends on what you do with the algae afterwards. If you're using it in a similar way to, say, biomass and bio-CCS, then that would be different. I'm not aware of that happening on a large scale, but I know it's certainly of interest. But it seems like Luke Perkmans knows a bit about the subject in terms of land-based cultivation of algae.
Yeah, Luke, do you want to add something here to the discussion?
No, not so much. It was just to clarify that it's indeed land-based, that there is ideas to capture CO2 from power plants and use that CO2 to grow algae. But as you mentioned, the whole carbon accounting thing depends on what you then do with the algae.
Yeah, and I would think that if you've already captured the carbon, just to add on that, it would be more efficient to store it or utilize it for another purpose than trying to grow the algae on it to begin with.
Yeah,
but
that's always the discussion. And also for algae, do you want to use them for energy or for higher value products? Probably the higher value products are more useful. So
I would tend to agree.
Thank you. Good. So then, Job, you were mentioning, and you showed us this carbon capture map, where we can see that there's a lot of projects coming on. I think you said something like, yes, the market is growing, but it is starting late. Did I get that right? So it should have started earlier and it needs to go faster, or what is the tendency here? Is the market picking up in the pace that it should be?
Yeah, sure. I can share a bit with my background, because actually I've been working in Brussels since over a decade now, and I started here as a correspondent, writing about climate and energy policies, and one of the topics that I covered was CCS. And back then already, the sense was that this sector had a lot of potential, but was not coming off the ground. But there were some promising projects that also received a lot of EU funding, a bit like with the hydrogen sector. And actually, all of those projects were shelved or cancelled in the years after that. And this industry has been going through a bit of a winter with just a lack of investment, a lot of prospects, and cancellation of projects. Though even the technology for CCS is proven. For instance, in Norway, CO2 is being captured already for a few decades now, and stored. I mean, it's also completely safe. So there's really no reason why it should not really take off soon, at least on paper. But the problem is the cost of the capturing and the storage. But now we see that. So what has changed, and it's really interesting, is of course Paris, and the Paris Climate Agreement stipulated we need to stay at 1.5 degree global warming, which is of course now becoming incredibly difficult. But this is still the target, and we need to keep it alive, and maybe also with negative emissions. And actually, only with negative emissions we can actually stay within the limits. So there was limits, and so there was already, let's say, since Paris, a growing awareness also among policymakers that we had to do more. And then in the years following that, we've already seen a massive deployment of renewable technologies. I've also worked in the renewable energy sector for a number of years, and that sector is now really booming, which is great. But as this been also mentioned several times here, is that if we really want to clean up our entire economy, then you cannot do everything with electrification. So I'm really a big proponent of the massive electrification, let's say, theory or school of thought, and then everything that you cannot electrify, including, for instance, heat pumps, industrial heat pumps, but also using green hydrogen for industrial applications. There are still, and all the international bodies that matter have recognized that you still need to capture and store some of the CO2 in those hard to abate sectors, and then indeed in the end create negative emissions. Well, that awareness has then landed since 2018 to 20, and now with the European climate law, this has been a real driving force, I would say. And then, of course, now with the upcoming 2040 target, we're going to go for probably 90% greenhouse gas reduction in 2040. You really need to start looking at CCS. Once again, there have been no major breakthroughs in the technology, but now the sense of urgency is so much bigger, and now we also see more and more funding coming available, also from the side from the Commission. Public-private partnerships in the Netherlands and in Norway, and a lot of countries, including Denmark, really pivoting on CO2 storage. We also see that in countries like Germany, Spain, and even in Austria, which has always been dead against CO2 storage, and that the tide is now really turning, and that all these countries are repositioning themselves on their CCS policies and developing new strategies. So it's really a very fascinating time to be working in this business.
I agree. Thank you. And then I have a question to Janneke. So from your industry perspective, what are the main barriers to the deployment of these technologies at the moment, and what needs to happen so that you have green light again and this will see a massive deployment?
Yeah, I think as Jens mentioned also, the technology is basically there. It's been tested thoroughly. We know that it works. I think that the challenge is that it's still early in the development. There's very few projects, and the price is still higher than the cost of emitting this CO2. So this industry is still dependent on some sort of a public funding to close the gap for these early projects. So we will need a development towards more energy efficient and space efficient projects, learning when it comes to integration into existing industrial plants, and of course the infrastructure for transport and storage will also contribute when this is expanding and developing. This will also contribute to reducing costs. So I would say that the main challenge is not the actual capture technology. It's more about the whole structure, the costs, and the transport and storage part. And if I may add one thing also, it's always about the hen and the egg. Nobody wants to develop a capture project before they know that they can actually have a solution for this CO2. And at the same time, the transport and storage projects are kind of waiting for the capture projects to move along. So it's always it's also about coordinating these all projects along the value chain.
Okay, so we also need to develop the transport and storage part of it, and not just the capturing. Yes, and then I see, Job's comment here that Equinor is working on ocean carbon storage. Yeah, thank you. Jens, anything to add to the barriers or to what needs to happen?
Yeah, of course. And I mean, a lot of it has been said already, and there's nothing I would disagree with. And I think the question is really, I mean, actually the carbon capture plant, to be quite honest, I mean, yes, it's expensive, but it's quite straightforward project development for companies like us, right? I mean, we are used to also build and develop multi-billion euro power stations. So this is also something we can do, and we're good at it. And we also have the experience also with the carbon capture plant. But the real thing is really the infrastructure, and especially the infrastructure, because it's also not only one company that can do it, but also not only one country that can do it. But in the end, it's a cross-national challenge that we have. And talking about the cross-national challenge that it is, it's both about the infrastructure, which is a hen and egg problem, but it's also about the whole regulatory environment. If, for example, you pick the Netherlands, and also you just mentioned that we need to have some funding scheme or some incentives out there, is also true. But for example, just a very practical problem. A lot of the funding schemes, for example, STE++, which is a Dutch funding scheme for basically renewable or sustainable energy transition, and it well, first of all, it excludes at this moment BECCS in the electricity. We focus more on the industry, which is a shame because the bigger potential is in the electricity. But also, it will only allow for projects that are in the Netherlands. But most of the storage is currently developed outside of the Netherlands, which is, for example, Norway, the UK, or Denmark, or whatever. So the point is that already you get to a point where, there's barriers, regulatory barriers, incentivizing barriers, but also the hen egg problems that stand in that way. And if I would need to put a headline above it, then it's also about speeding up, because everybody thinks that 2030 is far away and that 2040, of course, is super far away. But if you want to develop infrastructures like this and transition pathways like this takes time. And so we need to start early, and instead of making too many fancy PowerPoints and too many fancy plans, we need a couple of partners to put them together and to really create those value chains also on a really large scale to also prove that it works. And looking at that companies, but also institutions need to speed up. For example, at the moment, the European Union is developing their own carbon removal framework, but they're taking again too much time. So companies, also like our company, we're forced into developing our own methodologies together with partners, for example, CCS Plus Initiative and others, to come up with something to create and kickstart that market that is going to be, or that is already a voluntary market in the beginning, but still quite small, and it needs to grow into a compliance market. And here again, industry is faster than politics, but we need the politics to ease and pave that way. So it's all about a combined effort and speeding up our game.
Thank you, Jens. So that was almost some closing words already. So I think we're gonna see a lot more developments here in the near future. I think the ETIP ZEP, the Zero Emissions Platform, has an important role to play here to enable some of these things, but also projects like the NEGEM project that Alana mentioned, do their share, and we will see more research and development projects and more demonstrations in the near future. I think before everybody has to go to their next meetings, as this happens nowadays